Hi, welcome back. In today's video, we're going to talk about our last attribute of rational functions, which is horizontal asymptotes. Now, horizontal asymptotes behave very similarly to vertical asymptotes, but instead of our function having a vertical dotted line, we're going to now see a horizontal dotted line, right? It'll be an imaginary horizontal axis that'll also behave like a boundary, very similar, right? But it's now a horizontal component. Now there is a small difference between a horizontal asymptote and a vertical asymptote, and we will get to that, right? But for this type of function, whenever we're dealing with the function, we're going to, let's say we have we'll call this a top exponent, we have some sort of function on top, we have some other function in the bottom, right? Our goal when we're looking at a rational function is we're going to be comparing the highest degree, right? The highest exponent in the numerator and the highest exponent in the denominator. The comparison of these two exponents is what's going to help me figure out my three rules. I have three rules for horizontal asymptotes. I will discuss two of those in this video, and then in the next video I will talk about the third rule specifically on its own. But I will address it here so you can have an idea of what we're talking about. Alright, as usual, don't forget to like and subscribe. Feel free to pause the video and take some notes with me, and we'll see you at the end. Let's get started. Alright, so here we have our first scenario, right? The first rule that I want to talk about is what happens, and I'll write it here, I guess, on the side. As usual, we're going to want to simplify the function as much as possible. Here, there's something to simplify, so I'm going to get going. Notice how the top exponent is equal to the bottom exponent, right? I have the highest degree here is technically x to the 1 power, and the bottom here, the highest exponent is x to the 1 power. Since they match, I'm going to take the ratio of the coefficients. So let's say that we have, as I showed you earlier, right? I have a general function on top and on the bottom. Let's write a generic scenario here. So f of x equals ax to the top exponent plus whatever's left over divided by bx to the bottom exponent plus whatever's left over. Since the top equals the bottom, I'm going to take the ratio of the coefficients as my horizontal asymptote. What does that mean? It means that I have here a 2 as a coefficient and a 1x as a coefficient. So in front, the ratio of these two has a horizontal asymptote at y equals 2 over 1, or just 2. So I'm going to go to y equals 2, and I'm going to make a dotted line here. That is horizontal. Yeah. The ratio of the coefficients will give me my horizontal asymptote. Now notice how for horizontal asymptote we use y equals as opposed to x equals. Right? The horizontal asymptote crosses the y-axis. So we say y equals whatever the asymptote is. For vertical asymptotes, if you remember, we dealt with x equals some number because the vertical asymptote crossed the x-axis. It was an imaginary line that goes vertical as opposed to horizontal. Now, what does that mean here with our graph? Well, we still have a vertical asymptote here, if we recall, right? From a previous video, vertical asymptote here will be at x equals -1. So I have an imaginary line going through -1 as well, vertically. And this kind of divides the problem into like quadrants, right? Now, from the graph, because I know the graph already, and if we were to find the x-intercepts, the holes, the y-intercepts, all that information, we would be able to tell that the graph looks like this. And on the other side, it would be going upward in this direction. Right? Notice how now we have a vertical boundary that the function is going to get really close to and never cross, and a horizontal boundary. What horizontal asymptotes tell us is what happens as a function goes to negative infinity, and positive infinity. Where is it tending to go towards? Well, it's going to get really, really close to that positive 2. To the left, it's going to go all the way down to as close as it can to 2, and on the right, as close as it can to 2 as well as an output. All right, so let's do another example. Now notice how the top exponent matches the bottom exponent. We're going to use the ratio of the coefficients. Now, it's safe to say that I can do this right now and find the horizontal asymptote at y equals 2 divided by 4 is 1/2, which is the ratio of the coefficients. But just to be safe and just to be sure, we want to simplify the rational function, right? Which means I have to simplify the numerator, the denominator, factor, see if we have any holes. All that information is still going to be needed when you're solving a problem. So let's start with that. Let's start by simplifying, right? Divide everything on top by 2. When you factor out 2, it simplifies the quadratic. In the bottom, they're both divisible by 4, so take out the 4. This gives me x squared minus 4. Now I can factor out the numerator. X plus 2 times x plus 1 divided by 4. And here we get x minus 2, x plus 2. As the function simplifies, notice how we're left with 2 times x plus 1 over 4 times x minus 2. Right? This lets me know that there's only one vertical asymptote versus 2 vertical asymptotes. Right? So vertical asymptote related, I know that it's going to be at x equals 2. And I can sort of graph that already so that I can see the vertical boundary. Right? I can distribute if I like. Right? The function is simplified as 2x plus 2 divided by 4x minus 8. Notice how the numerator matches the denominator. So I can use the ratio of the coefficients here. So y equals 2 over 4 or 1/2. So I can go to y equals 1/2, and there's my imaginary horizontal asymptote. Now in this case, it so happened that it matches, right? The original function and the simplified function match. And that will happen most of the time, right? But what this doesn't tell you is that there is a hole here at x equals -2. It doesn't tell you about the vertical asymptote. There's a lot of things that it doesn't tell you. And it's also good to make sure that once it's simplified, we are in fact left with the same ratio. Yeah. Now, because I know this function, and I'm not going to focus on graphing all the other components to it, I can tell you that it'll cross down here. It'll get really close to this line. I'll do this in a different color. It'll go really close towards the bottom. And this isn't as specific or as detailed as I can make it, right? But the goal for this video is horizontal asymptotes, right? I can get more specific with the x-intercepts, y-intercepts, all that kind of information. For now, can we identify the horizontal dotted line at 1/2, right? So, to recap for this first rule, whenever the top exponent matches the bottom exponent, right? The highest exponent in the numerator and the denominator, we're going to use the ratio of the coefficients as my horizontal asymptote. So whatever the ratio is, the line can move up positive to negative. It can move all around, right? Let's talk about our next rule. I'm going to simplify the problem first, and then we can talk about what rule this is, right? So rule number 2, we're going to compare the numerator and the denominator for exponents, but I'm going to first factor out a little bit. I can simplify by factoring out a 2. This turns into x minus 2 divided by x minus 2, x plus 2. This lets me know that there's going to be a hole at x equals 2, and then my vertical asymptote will be at x equals -2, right? I have this sort of picture going. Now, notice how I'm left with 2 divided by x plus 2. Well, what is the highest exponent that I have on the numerator? On the numerator, there's no variable with exponents, so technically I have x to the 0 power. There's 0 x's on top, and there's 1 x in the bottom. Notice how for this problem, the numerator is less than the denominator. So top is less than the bottom. Here's my rule. The top exponent will be less than the bottom exponent. And even before simplifying it, notice how x to the 1 power was still less than x to the 2nd power. Right? Since it's less, now we're going to say that the horizontal asymptote is at y equals 0. Now the imaginary line will be right on the x-axis. It'll be y equals 0. Yeah. And the graph will look something like this when we graph it. I'm not going to draw the holes or all the information, right? But it'll go through. I have my vertical boundary. And then my horizontal boundary will be the 0 line. So it'll get really close to it, but not touch it. And then over here, very similarly, it'll go downward to approach the vertical line and approach the horizontal line. So what happens as the function goes to positive infinity and negative infinity? It's going to approach 0 as y, as the output. Right? So my horizontal asymptote is y equals 0. Now, I do want to show you, right, how sometimes, well, actually, let's do another example. Yeah, let's talk about another example using this rule. Notice how the top exponent is already less than the bottom exponent. So top is less than the bottom. I already know that the horizontal asymptote will be at y equals 0. It'll be a horizontal line right through the origin, through y equals 0. Yeah, it's my imaginary line. Now let's simplify a little bit just to make sure that we account for holes and vertical asymptotes and all that kind of stuff. Here we have x minus 4 on top. In the denominator, they're both divisible by 2, which makes this 2x squared minus 16, which means I can now factor this right here as 2 times x minus 4, x plus 4. Now, since the top is grouped together, right, technically, I can now cancel those two, and I have a hole at x equals 4. I have one vertical asymptote at x equals negative 4. So I have an imaginary line for this one at negative 4. Right through here. And this simplifies to 1 over 2 times x plus 4. Notice how the numerator is still the x variable, right? There's 0 x's. It's still less than the denominator has 1 x. So my horizontal asymptote is at y equals 0. Now my graph will look something like this. It'll be below, above. Now to find those specifics, right, I would be considering holes, x and y intercepts. I would find the actual points, right? And if I need more points, I would plot a table, and I would plug in numbers into my function to determine where exactly are those points. This is just a sketch so that you can see how this behaves, right? Now, for all these examples, we've had only one vertical asymptote. I want to show you how sometimes when you have multiple vertical asymptotes, like here we have two vertical asymptotes, right? We have an imaginary dotted line here. It looks like it's touching it, but it doesn't, because we just got to zoom in some more to see that. The horizontal asymptote is still going to be 0. I'm wondering if this might be a better color. Right, my horizontal asymptote is still y equals 0 for both. But sometimes when we have multiple vertical asymptotes, sometimes in the middle, it won't cross it or it will. And for horizontal asymptotes, it's okay to cross the boundary. Horizontal asymptotes describe end behavior. This is really the main focus of the function. What happens at positive infinity and what happens at negative infinity? In the long run, what is the function doing? And notice how it's still getting closer and closer to 0 on both sides. Whether it's coming from the top, right? Up here, it's getting closer and closer to 0. The middle, it might do some funky stuff. And that can change, right? And that usually happens the more vertical asymptotes you have. When you have only one vertical asymptote, it won't cross the horizontal, right? It's when you have 2 or more. But notice how the rule here, right? The top exponent is still less than the bottom exponent. There's 0 here on top, so the top is less than the bottom. And that's our second rule, right? When the top